maybe you're curious. You come up with a design. You have the phase 1. And they give you the phase 2. Now, right now, you give me the phase 2. Now we work in the phase 3. You still have doubt about your design. And in my case, if you show me your design, you have many solutions, many ways. Okay, don't have unique design, one single design for the system that you try to build. Okay, maybe might have different designs. Okay, so one thing you can think about, you can use the normalization. So it give you like a design, and you can't tell whether your design is good design or not. Based on what? Based on the given set of rules. So when you talk about the normalization, the database design technique that reduce the data redundancy and eliminate undesirable anomalies, insertion, deletion, modification of the data. Okay? So it looks like we have what? We have rules which allow me in order to divide the large tables into smaller tables and link them using the relationship. If you follow the exact techniques that we follow in order to compute the ER diagram, maybe you don't need this normalization in most of the cases. Actually, 95%, if you follow the exact steps in the ER diagram, you don't need to have the normalization because your design is going to be already normalized. I'm going to show you which level is going to be normalized or which specific rule, which normalized form. But since we're still learning, maybe we're going to make a mistake. Okay? So it's a good idea to check this one. I need to have another idea, another way in order to test whether my design is good design or not. We're going to give you like some kind of competence, yeah? So that's why we're going to take a look at normalization. How can you do this one? The normalization is going to follow what is called the normal forms. So I do have like set of normal forms, okay? Set of rules, okay? With the properties that the relation must satisfy. I do have 6 different normal forms. For every single normal form, I'm going to say like each normal form has properties, must be satisfied in order to tell whether your design or your relations are following this normal form or not. Okay? So what we're going to do here, check the relation out. Every single relation that we have, for example, I have 6 relations for my designs. For each relation that you have, you need to check whether this one good design or not. What do you mean? How to can tell whether it's going to be good form or not? Whether it's going to satisfy a specific normal form or not. What do you mean normal form? Again, is like set of rules or properties that the relation must satisfy. For example, we don't have the composite attributes. For example, it doesn't have multivariate attributes, something like this kind of condition that we're going to take along. If this one satisfies this one, I can say, oh, this satisfies this normal form. It depends what normal form you're going to have because we have 6 different forms. Which one you try to achieve? I'm going to tell you exactly which one you need to do. Okay, what's the exact one? So you check this one. If you found one relation or any relation that doesn't satisfy this set of rules, you need to do what? You need to decompose this one. You have a problem here. I need to fix it. How to fix this one? I'm going to decompose this relation into sub-relation. Each of these sub-relations must satisfy this set of rules defined by this normal form. Okay? If not, decompose this one. Continue this operation. Good? So again, each relation is going to be in good form. At the same time, the decomposition must be lossless decomposition. Okay? Not lossy. Using functional dependency in order to help me to how to achieve this goal. So let's take a look at the normal form or the normalization. Actually, as I mentioned, we do have 6 normal forms. In most case application, most design, it's enough to have up to this level. Maybe you can do Boise called normal form, but in most cases, this one is satisfied. So in your class project, once the end of the semester, I don't care about right now. As I mentioned, I care about your job, but I don't care about the time right now. In order to make sure that you understand the material, in order to have a kind of confidence, certain confidence that your design is good, design. Make sure that your design must satisfy the 3rd normal form. I'm going to go over, still have time. I'm going to show you what do you mean the 1st normal form. How can you test this one? How can you test this one going to be the 2nd normal form? And how can you test whether my design 3rd normal form or not? And how can you fix? Okay? The 4th, the 5th, and 6th is not required in most cases. Okay? So, what does that mean? If you take a look at the graph here, at the beginning by the way, we can do this one, but I don't like this technique. But one technique to put all the attributes in one relation. Then starting breaking down this one. That one way it works sometimes. So here the whole relation is going to be one relation. Then after that, check whether it's going to be in the 1st normal form or not. Okay? In order to satisfy the 2nd normal form, this relation, for example, must be in the 1st normal form first, plus something extra. So you're going down, you're adding more restriction, more constraint, more rules. Okay? So you see, for the 3rd normal form, that means The relation must be in the second normal form. Of course, in the second normal form must be in the first normal form plus one attribute set of condition here. Plus, we have another extra constraint here. We keeping adding constraints set of all in order to specify what kind of normal form that we're looking for, and etc. Okay. So let me start with the first one. This is the easy thing. How can you tell my relation is the first normal form? That means all table are flat in general. That means relation scheme R in the first normal form F, it doesn't have any composite or multivariate attribute in this relation. It's easy. There is no composite attribute, there is no multivariate attribute. Which one that you did when you transfer from the ER diagram to the corresponding relational model? What we did here, relation table. If you have a composite attribute, you have to put this one separate attribute for each composite attribute. If you have a multivariate attribute, what we did, you create separate relation for this multivariate attribute plus the primary key of the relation, and both of them going to be primary key of the relation. The same thing, we're going to achieve this one. If you follow that step, or here, both of them will be giving the same thing. So here you can check whether this is the condition that we have, okay? Must be in the normal form. F, every attribute of the relation is single value attribute. It's not multivariate attribute, it's not composite. Let's give you an example. Assume that this is my table. Name, it might be have a composite attribute, and we still have a skill, it's going to have multivariate attribute. Of course, if you have a data, it's going to help you a lot. Because if you have simple data with the data table that we have, if you fill this one with the table with the data, then you start looking at the relations here. Makes sense to you. It's not in the first normal form because it doesn't satisfy the condition. How can you fix it? I do have two ways to fix this one. Let's start with one at a time, actually. So the first way to get performed here is like solution for the composite attribute first. It's easy. The composite attribute do what? Insert a separate attribute in the relation for each sub-attributes of the composite attribute. Okay? So for the last name, I'm going to want separate attribute. For the first name, I'm going to have a separate attribute. Done. So I fixed this the way how to fix the composite attribute. And this is the way the exact that we did before. Good. How about the multivariate attribute? I'm going to show you two different solutions. The first one, I'm going to do what? You can determine what the maximum number of skills will get. How many maximum skills that you expect in the day? This is one solution. Maybe not good, but it's a solution. Okay? How many skills? Maybe we have only at most 2 skills for each employee. Okay. So that means if you have a multi-value maximum number of 2, that means I'm going to generate 2 separate attributes in this case to store the skills. So skill 1, skill 2. If you have a 5, that means you have 5 columns. Okay? So this one for each of them, I end up with something like this. If we take a look at this one, actually this is fine. Kind of, right? Still have something we call repeating groups, with this is defined as a set of logically related fields or values that occur multiple times in the record. So you see that you have Java, and still this column. This column is going to repeat the group because it's going to be, conceptually the same attributes. We still talk about the skill. Okay. So in this case, for every single one, you need to have like a separate tuple in this case. There is another thing. If you take a look one question, maybe someone's gonna say and still argue, say, but it's fine. I can't keep this one. Actually, you can't keep something like this. But there is another problem here. If you have, for example, multiple scales, for example, the maximum number of scales, for example, 5 or 6, we cannot guarantee every single user is gonna have 5 or 6 scales. So we're gonna have many empty or null values. Another thing. And if you try to find the search for the scale, required for me to ask multiple columns in order to find the scale, right? They have it different. So the other thing here, which one is going to be? Why you put Python before Java? Why you didn't put Java before Python here? Or the MySQL, Postgres, Addison. You see that? We keep asking, so it looks like we are not satisfied with this one. So to bring the model, the first normal form, although this one does violate, we can ensure that no tuple contains more than one skill in order also to avoid what's called the repeating groups. So now we have only one column for each tuple or row or tuple, which is gonna satisfy, we're gonna talk about, represent, say the skill. That's what we did here. Okay? The other solution here is called, in this case, yeah, by the way, you need to update the primary key. The primary key in this case is going to be what? The employee ID and the skill. Okay, because it's not employee ID, we have maybe be this one, so the primary key we have it because we have 2 skills or maybe more. The second approach, which is the one that we agree that we believe that's maybe the best. You can start with I'm talking about the multi-value attribute. You start to what? You move the multi-value attribute that violates the first normal form and placed in the separate relation. So I do have a problem with the skill. Yeah. Oh, this multi-value attribute. Take the skill here. Take the primary key of the relation. Put them in a separate relation. And both of them can be the primary key, and you remove this one here. And that's what we did here. You see that? That's what we have here. Okay? Actually, you can stop here. Up to here is fine. There is no problem. But you can have another way to do that. Don't worry, in the second normal form, we're going to end up, we have something like this. Okay? So this is the first normal form. Just I want to, just to make sure that we still understand, remember the candidate key, the super key. Okay? So the super key is what? It's going to be the set of function dependency F. F is going to be set of function dependency that, R is the relation. Okay, given the set of function dependency F, and we have a relation R, you can say, for example, K is going to be super key of the relation R, yeah, and K is going to be super candidate key if K is minimal, yeah, and that's what we did here. Okay. Here's how to do this one. Actually, we covered this one, so there's no need to talk about this one. The most important thing I need to talk about the prime and non-prime attributes. When you find out you have a set of candidate key, maybe you have more than one candidate key. Okay, so for example, assume that A, B determines C, D, F. Okay, and the relation R is going to be A, B, C, D, F. Okay, so and this is the candidate key. I can the list of attributes, the set of attributes that belongs to the candidate key, we call this one prime attribute. The set of attributes that belongs to none, that wasn't part of any candidate key, we call this one non-prime attribute. Okay? This one is going to be help us a lot. If you find any set of attributes in your table, okay, that depends only on part of the candidate key. For example, if you found you have any set of table or function dependency here, for example, CD. CD depends on one in A. A is prime attribute. A is a part of the key, not the entire key. We call this one, we have any non-prime attribute that depends only on a part of the key, not the entire key. We call this one partial dependency. Okay, that's what's called partial dependency. We don't like this one, and I'm going to show you why. So the second normal form is going to say what in this case? It should be in the first normal form, and there is no non-prime attribute. Depends on the part or subset of the candidate key. In other words, we don't have a partial dependency. Why the partial dependency is bad? The partial dependency, that means you put a lot of information, or the information doesn't relate it to the entire key. If you have a subset of attributes in your table that does rely completely on the entire key, only on the part of the key, that means this one must be moved somewhere else, because here we're going to have some redundancy. I'll give you an example here. So anyway, in this case, must be the first normal form, composite, there is no composite, there is no multivariate attributes, and also there is no partial dependency. Let's have an example here. I give you something like this, okay? A, B determines C, D, A determines C, and B determines D. We do have only A, B as a candidate key. If you check this one, A, B closure, you're going to end up at A, B, C, D. Yeah? A closure is going to be A, C, done. B closure itself is equal to B, D, done. So in this case, there is no R, is not equal to R, not equal to R, not equal to R. So R, so this is going to be super key and the candidate key. So the prime attribute is going to be AB, the prime, Non-prime attribute is going to be CD in this case, right? Okay, take a look. This is the whole key. Non-prime attribute depends on the entire key. Good. Non-prime attribute depends on part of the key. Non-prime attribute depends on the part of the key. So we do have a problem here. So that means it looks like you put too much information that doesn't belong to each other. That's the meaning here. Okay? So let me give you an example here. It's going to be much clearer here. First, assume I do have an advisor. An advisor is going to have the instructor ID, student ID, instructor name, student name. I put this one in one table. In the first normal form, there is no composite attribute, there is no multi-valid attribute. Okay, good. It's not in the second normal form. Why? Because the key that we have is instructor ID and the student ID. If we assume that student may be advised by multiple, let's say, instructors. So in this case, we're gonna record the student ID or name many times. Okay? So in this case, what's the problem here? This is the key instructor ID and the student ID, but we have the instructor name is going to depend on the instructor ID, and the student name only depends on the student ID, which is going to be like partial dependency. Non-prime attribute depends only on part of the key. We don't like it. Why? Because it's going to have some redundancy. You see that data is going to be redundant. So in order to fix this one, what we're going to do here, take a look where you have the problem here. Let's show you here. The problem now, the function depends said, okay, this one depends on this one, and this one depends on one. So that means take the non-prime attribute, move in another table, so it's going to be student name, and take the prime attribute that we have, that partial the part key that this attribute belongs to, depends on, add here, the student ID here, put the new table, and then the part of the prime key or the prime attribute is going to be what attribute to be key here. You move this one here, and the same one for the instructor ID. You take the instructor name here with instructor ID, another relation. The prime key is going to be instructor ID. Then I'm going to remove the instructor name here. So you see that I remove the redundancy of the data. Let's take a look at the table that we have. Assume that that's what you have. As I mentioned, the first approach in order to handle the, let's say, the multi-valid attribute, it's acceptable if you have something like this. Take a look here. What do you have here? What's the key? You can check your design using this. Okay, I want to make sure this is in the second normal form now. Check this one. Okay, employee ID and the skill, they are what the key. I noticed something here. The name, the job, and the department and the ID, it depends only on the employee ID. Do you think this information depends on the skill? No. So those are the set of non-prime attributes, depends on the partial dependency. It has the only part of the candidate key, not the entire key. Because here the candidate key that we have employee ID is skill, but non-prime attribute depends on only part of the key. So in this case, you need to move them. You didn't need this over. And see, they have redundancy programming one. If you have 5 skills, we're going to repeat this one 5 times. If you have 5 skills for this one, we're going to repeat this one 5 times. This information is going to be repeated. Why you need all of them here repeated? Doesn't make sense. So in this case, since we have this function dependency, you see that when I was using the function dependency, say employee ID is determined as name, job, and the department. ID, non-prime attribute depends on the part of the key. So move this non-prime attributes in new table. I move them in new table. I remove this one. Take the part of the key that on prime attribute that depends on these attributes depends on. Add this one to this table. Don't remove it. Add it. Make this one gonna be the primary key of this one new relation. And now we end up, we have this one. So this one gonna be the leftover, gonna be employee ID skill, and we have the other table that contains the employee ID, name, and job and department. All of them depends on what? The primary key here. And here, since all of them gonna be, I mean, both of them primary key, so we don't have problem. So this one gonna be in the second normal form, this one second normal form, and you see, we get rid of the redundancy of the data. Make sense? I still have time to go over the third normal form because that's what I want for me to do. If someone say whether the second normal form is enough or not, because it makes sense to me. I'm done. There is no redundancy. We still have an issue here. Give you, for example, a structure that have name, assume the name, the A, or the say the unique identifier, or the primary key here in this case, or candidate key is going to be the name. So it's the name of structure, salary, department name, and the budget. Okay. So I give you this kind of functional dependencies. Okay. The name is going to uniquely identify the, say, B, C, and D. Good. And C determines D. So take a look here. You see it. Non-prime attribute, it depends on the prime attribute, and the candidate key is going to be A, which is going to be, this is the prime. So there's no partial dependency. It's the second normal form. We do have a problem here. You see that what's D and C? Both of them non-prime attributes. So I do have non-prime attribute determine another non-prime attribute. You see that here, C and D, which is here, the department name is going to determine the budget. Both of them non-prime attributes in this relation. It's in the second normal form. But we still have a problem. We still have redundancy, right? If you take a look at the department name, repeat it, for example, we have multiple instructors, or many instructors belong to the same department. So we're going to have, for example, computer science 50 times, and we're going to repeat the budget 50 times. And we have a problem. We still have redundancy. What does it mean if you found in your relation you have, or the table that we have, non-prime attribute, it depends on another non-prime attribute? That means you put too much information. Because you end up, you have like update anomalies here. Yeah? So you put too much information. That means definitely these non-prime attributes must be somewhere, belongs to another relation. That's what is called the third normal form. The third normal form is that must be in the second normal form, and all the next normal form must be in the first normal form plus more. There is no partial dependency. And also, we don't have what is called transitive amide dependency. That means we don't have non-prime attribute depends on another or non-prime attribute. It's not allowed. If you have this one, this means it's not in the third normal form. How can you fix it? You see that? That means you put too much information in one place. So in order to fix, or in order to test first, how can you tell whether it's going to be in the third normal form? This simple test, the simple one, make sure, for example, for every single functional dependency that we have, alpha determines beta. Check whether it's going to be trivial or not. Beta subset of alpha. Or the left-hand side is going to be, let's say, primary, or say super key, so we don't have a problem. Or the right-hand side is going to be part of the candidate key. So in other words, there is no prime attribute, non-prime attribute is going to be depends on non-prime attributes. In order to fix that, that's what we're going to perform here. Check which is the one non-prime attribute that belongs to non-prime attributes. Okay? If you found this one, remove these depends non-prime attributes that violate the third normal form, and place them in the separate relation. So in this case, we have the department name, and we have a budget, and it's going to be in the separate relation. Okay? And the primary attribute is going to be the non-prime attribute that we have. And remember, what I remove only the right-hand side. So the department name is still going to be in the original relation. We have, I think we have a name, we have, I don't remember, then we have the department name here. So I know here, we have department determines the budget, non-prime attribute determines another non-prime attribute. Take the one on the right-hand side, move to another relation, and copy the left-hand side because I need to keep the left-hand side there. Another relation. So you see that we have here name, we have the department name, for example, GPA, whatever the department name, and in another relation we have the department name and the budget. So we don't have redundancy in the data. So hopefully that makes sense. Okay? Actually, that's all I need to cover. Okay? I expect from you to try to apply this one toward your class project, even after the class project, end of the semester, in order to make sure that your design is correct. There is no redundancy. And this one is going to solve all your problems if you have up to the third normal form. Make sure that your data or design you have, at least you have up to the third normal form. Then you are fine in this case. Okay? So that's all